How we doing, guys? We're looking at page 212, 213, exercise 12G. These are questions that require the chain rule. Um, now, just to start off with, if you go to your log tables to page 25, you'll see the chain rule given here, where if some function is given by u, then the derivative of that function, so I'm going to call that du dx in my version, du dx is du dv times dv dx. Okay, and we're taking that as a given. We're working with that. But what we're noticing about it is that we take du dx and we introduce this other variable dv. Okay, so it takes a 2-variable problem and changes it into a 3-variable problem in some ways. Now, there's a useful trick with the chain rule is to think of it as a fraction. If that was something like 5 over 3 and you want to introduce some other variable, you could say, well, that's the same as 5 over 3 multiplied by, let's say, 8, top and bottom. Okay, so it's the same as 40 over 24, which is true for fractions, and it looks the same for the chain rule. It's not the same. It's very much not the same. You're using the chain rule here. You're not using anything really to do with fractions. This is to do with rates. But because it's so useful, that trick of thinking you're multiplying top and bottom by 8 here or by dv here, we're going to kind of refer to it as though that is how we're working. Okay, so very often you're going to see something like, well, over here, you're going to be working with ds dt, and you're going to change that. That's going to be dv dt. I'll show you why in a second. And you're going to want to introduce that other variable s. You're going to say, well, dv dt, the chain rule says, I'll do this in red, a new variable ds top and bottom. That's what's going to be useful about this. Okay, now you'll see that in context here in question 2. So we're on page 213. Question 2 asks us, solve this second order differential equation. That's second order because you're differentiating twice, given that these initial conditions. Okay, so here's the equation. d2s dt squared is 9s given these initial conditions. So for these second order differential equations, you're going to say d dt of ds dt. That's just another way of saying the second derivative is 9s. Differentiate twice, and then once, and then twice. And then we're going to make a substitution. We're going to say let v be this ds dt. Okay, which is nearly a variable in our own right. If you look up here, it was one of our initial conditions is ds dt. So by letting v equal ds dt, we are going to get ourselves dv dt needs to equal 9s. Now this is good because it's now a first order linear differential equation and we know what to do with them usually. But it's bad because look, you've got 3 variables, v, t, and s. Okay, you only ever really want 2. So this is where we break this up. We use our chain rule. We come over here and we say, well, actually the chain rule lets me break that up into dv dt equals 9s. It lets me introduce this other variable, okay, which in our case is s. So ds and ds is what I want there. Okay, now ds dt we already have a name for. So that becomes v multiplied by dv ds equals 9s. And look what's happened now. You've only got 2 variables in a first order linear differential equation. Okay, so separating it out, we're going to say v dv equals 9s ds. Integrate both sides. And we're going to get ourselves v squared over 2 equals 9s squared over 2 plus c, or v squared is 9s squared plus twice c. And then come up here. Our initial condition said v is minus 6 when s is 2. So that is going to give us minus 6 squared equals 9 times 2 squared plus 2c, or 36 equals 9 fours are 36 plus 2c. Okay, so we get c equals 0. And our equation now becomes v squared over 2 equals 9s squared over 2 plus 0. So let's rewrite that over here. V squared over 2 equals 9s squared over 2 plus 0. And multiplying through there, you get v squared by 2 equals 9s squared. And taking the square root, you get v is either plus 3s or minus 3s. Now, which one of these do you pick? Well, go back to your initial conditions. Okay, v is minus 6s when s equals 2. Okay, so v, if s is 2, v will be plus 6. So that's no good. It has to be minus 3s that we have to work with. Okay, now I hope I'm not moving too fast. You can pause the video and go back and watch bits if you're not sure about anything there, but we've gotten ourselves as far as v equals minus 3s, and v was just our name for ds dt. So ds dt is minus 3s. ds over s equals minus 3 dt. That's just separating out our two variables so that we can integrate. And in these second order ones, you're always integrating twice. So what do we get ourselves? Well, that's going to be the natural log of s equals minus 3t plus c. And we know from our initial conditions that s equals e when t equals 0. I'll just write that down in here again. So that says ln e equals minus 3 times 0 plus c. Well, ln e is 1 equals 0 plus c. So c equals 1. And we get ourselves that ln s equals minus 3t plus 1. And what we are looking for in this question, solve for s really. Okay, the initial question was posed in terms of s, so solve for s. So from here you'll say s equals e to the power of minus 3t plus 1. Okay, let's go double check that I've got that all right at the back. That's 12g. Sorry, no, 12g e to the power of 1 minus 3t. 1 minus 3t. Lovely. Okay, the second question I was going to look at is question 6. So question 6 states, solve d2x dt squared. Now I picked this one because there's a misprint in the book. d2s dt squared equals 3x squared over 2. Okay, the answer they've given at the back, if you work backwards on it, gets you 3x squared, not x cubed, over 2. Given the initial conditions, dx dt equals minus 8 when x equals 4 and t equals 0. So they're all true at the same time. So, first of all, second order differential equation, you don't want it to be second order, so d dt of ds dt equals, I'm going to call that 1.5 x squared. ds dt is what we're going to call v. Sorry, that's an x, excuse me. So dx dt is what we're going to call v, and that's going to crop up here as well. Okay, so that's our v equals up there. So this thing becomes dv dt equals 1.5x squared, and we're now down to our linear differential equation. However, we've got our three variables, so that's unfortunate. How do we get rid of that? We use the chain rule. Okay, dv dt is 1.5x squared. And what variable do we want to introduce over here? Well, it's this third one, x. So that becomes dx on the top, dx on the bottom. And look, there you've got v there. So the left hand side now becomes v multiplied by dv dx equals 1.5x squared. Okay, separating out our differential equation gives v dv equals 1.5x squared dx, and integrating both sides now gives us v squared over 2 equals 1.5x cubed over 3 plus some constant. Okay, and that disappears to give 0.5. So multiplying through by 2 here, we get v squared equals, well, 0.5 times 2 is x, 1x cubed plus 2c. Okay, so come back up here, we know that v is minus 8 when x is 4. So minus 8 squared equals 4 cubed plus 2 times some constant. Well, that just says 64 equals 64 plus 2c. So you get twice our constant equals 0. So what does our equation look like now? Coming back up here, it looks like v squared equals x cubed plus 0. Or v equals x to the power of 3 over 2. So that's taking square roots on both sides, or raising both sides to the power of 1/2. Okay. And now, v, remember, is just a substitution. So if we come back to dx dt instead of v equals x to the 3 over 2, what you have here is, I should have been careful there. That is plus or minus x to the 3 over 2 when you take the square roots on both sides here. Okay, so which one is it? We'll come back to our initial conditions. If let's do this up here, v equals plus, now to the power of 1/2 is the square root of x cubed. That's what that says. Well, does that work? When x is 4, the square root of 4 cubed is the square root of 64 is plus 8. No, that does not work. So the other one is v is minus the square root of x cubed. And when x is 4, that's going to be minus the square root of 64, which is minus 8. So that's the one that works. So here, maybe what I should have said there is plus, or v is minus x to the 3 over 2. I have to disregard this one. Does not fit the initial conditions, so I work with this. Okay, and then I come along and I say, well, v can be written as dx dt. So now we're down to a linear differential equation in just 2 variables. Okay, so we can solve that. That becomes dx over x to the 3 over 2 equals minus dt. Actually, before I go integrating, let me bring this up to the top. So that becomes x to the minus 3 over 2 dx equals minus dt. Now, integrating both sides, we are going to get ourselves, that side's easy, it's just t plus some constant. Here, integrate this So increase that by 1, you get x to the minus 1 over 2, and then divide by the new power. And here you get minus t plus some other constant. Okay, that minus a half is a bit messy. If we multiply top and bottom by minus 2 here, we'll get rid of that. So we get minus 2x to the minus a half on the top over minus 2 times minus a half is 1 equals minus t plus d. So let me rewrite that out. Minus 2x to the minus a half equals minus t plus d. And let me double check that I have everything there. Minus 2x and minus half. Or it might be easier to multiply through by minus 1. 2 x to the minus a half equals t minus some constant. Now what were our initial conditions? Well, we know that x equals 4 when t equals 0. So that becomes, to work out d, that becomes 2 times 4 to the minus a half equals 0 minus d. 4 to the minus a half. Well, minus is 1 over and a half is the square root of. So that's 1 over the square root of 4. So that becomes 2 times 1 over root 4 is minus d. And 1 over root 4 is 1 over 2. So a half times 2 is 1. So this equation here now reads minus 2x to the minus a half equals minus t minus 1, or 2x to the minus a half equals t plus 1. We want to get x by itself, so that becomes x to the minus a half equals t plus 1 over 2. Okay, or that is 1 over, I'm going to call that the square root of x. Okay, 1 over, because it's a minus to the power of a half, is the square root. So I'm going to invert both sides here, and I'm going to get 2 over t plus 1 equals root x over 1. And then squaring both sides finally gives us 2 over t plus 1 equals x. Oh, squared equals x. So there's our solution. That is the unknown. If you take x there and differentiate it twice, the answer you will get is 1.5 multiplied by x squared. Okay, and I would encourage you, if you have the patience after all of that, to differentiate this twice and see, do you get 3 over 2 times this thing squared, which is going to be 3 over 2 times 2 over t plus 1 to the power of 4. So d2x dt squared. See if you differentiate that twice, do you get 3 over 2 times 2 over t plus 1 to the power of 4. If you're going to do that, let me suggest you work with x equals 4 over t plus 1 squared equals 4 times t plus 1 to the minus 2. Okay, differentiate that. In fact, I'll do it now. If you're not interested, you can go ahead and do the work. But the first derivative here is going to be dx dt is minus 8 times t plus 1 to the reduced by 1 minus 3 multiplied by the chain rule says multiply by 1, which is the derivative of the thing inside the bracket. That's okay. The second derivative is minus 24 times t plus 1 to the reduced by 1 minus 4 multiplied by, according to the chain rule, the derivative of this thing, which is just 1. excuse me, that should have been a plus 24. Minus 3 by minus 8 is plus 24. Now, does that give us what we want? Well, there's t plus 1 to the minus 4. So 2 to the power of 4 is 4, 8, 16. Now, we don't have 16 there, we have 8. So let's try 24 is 3 over 2 times 16, is that right? 3/8, yeah. So that becomes 3 over 2 times 16 over t plus 1 to the power of 4, which is 3 over 2 times 2 over t plus 1, all to the power of 4, which is what we expected to see. That is 3 over 2 times, that's x squared. Okay, because if you square this, you're going to get 2 over t plus 1 to the power of 4. So that's what we were expecting. Okay, thanks guys.